Hello, my friends. Thank you very much for subscribing to our channel. The general formula for the Fibonacci sequence can be derived in several ways. Interestingly, the topic we discussed last Friday can directly inspire one of them. So today, we will take this opportunity to discuss how to do that. First, let's have a brief recap of what we discussed last Friday. We cut a rope with the length of 1 into k segments, and each time at the golden ratio point of an existing rope segment. The longest segment has the length Lk, and we aim to find the minimum value of k times Lk. Last time, we demonstrated that, to get the minimum value of k times Lk, we need to make the cuts group by group, and the amount of cuts in each group becomes the Fibonacci sequence Fm. After cut for m groups, we get Fm plus 1 rope segments with the length of phi to the mth power, and Fm rope segments with the length of phi to the power of m plus 1. Because the total length of the rope segment remains unchanged, and is always 1. So we get Fm plus 1 times phi to the mth power plus Fm times phi to the power of m plus 1 equals 1. We divide both sides of the equation by phi to the mth power, and we get a very important conclusion. Fm plus 1 plus phi times Fm equals phi to the minus mth power. We can repeat the proof of this conclusion in another way. Fm plus 1 plus phi times Fm. We can first separate Fm plus 1 into Fm plus Fm minus 1, and then plus phi times Fm. Merging the terms of Fm together, the coefficient is 1 plus phi. From the definition of golden ratio, it can be deduced that 1 plus phi is equal to phi to the power of minus 1. So Fm plus 1 plus phi times Fm is equal to itself multiplied by phi to the power of minus 1. So Fm plus 1 plus phi times Fm is a geometric sequence. The common ratio is phi to the power of minus 1. And the first term is F2 plus phi times F1. Both F2 and F1 are 1. So this is again 1 plus phi. That is, phi to the power of minus 1. Our target is to find the general formula. So both Fm and Fm plus 1 should be regarded as the unknown variables, and both phi and m should be regarded as known parameters. Then this is a linear equations in two variables. To find Fm, we'd better have another linear equations in these two variables. To this end, in a similar manner, we construct a new variable, Fm plus 1 plus x times Fm, and then transform it in the same way. Our expectation is that we can get another geometric sequence as in the previous case. The coefficient of Fm minus 1 is 1 plus x multiplied by x, which should be 1. We thus get a quadratic equation in one variable x. According to Vieta's formulas, the product of its two solutions is minus 1. One of which is the phi as we discussed earlier. Then the other solution must be minus 1 over phi. Or in other words, minus phi to the power of minus 1. We replace all the x with minus phi to the power of minus 1. The resulting common ratio is 1 minus phi to the power of minus 1. Going back to the nature of the golden ratio, 1 minus phi to the power of minus 1 is actually minus phi. So the common ratio is minus phi. The first term is F2 minus phi to the power of minus 1 multiplied by F1. Or in other words 1 minus phi to the power of minus 1. Which is still the same as the common ratio, equal to minus phi. Therefore, we get two linear equations about Fm plus 1 and Fm. It is very easy to solve them. By subtracting the second equation from the first one, we have, Fm is equal to, phi to the power of minus m minus the minus phi to the mth power, over phi plus phi to the power of minus 1. This is actually the general formula for the Fibonacci sequence. As we have this formula, we can even revisit a variable, Fm times phi to the power of m plus 2, which we discussed last Friday, by bringing in the general formula for the Fibonacci sequence. Its dependence on m is fully reflected by minus 1 to the mth power, and phi to the power of twice m. Since phi is between 0 and 1, phi to the power of twice m is close to 0 when m is large. Thus, we can get that, when m approaches to infinity, the value of this variable is close to the square of phi over phi plus 1 over phi. Due to the existence of minus 1 to the mth power, we can get that, when m is an odd number, Fm times phi to the power of m plus 2 is larger than this limit, and when m is an even number, it is smaller than this limit. by considering both -1 to the mth power and phi to the power of twice m at the same time. We get that the minimum value of fm times phi to the power of m plus 2 exists when m is equal to 2. Which is the same as the result we discussed on last Friday. Moreover, when m is equal to 1, we can get its maximum value. It must be noted that this maximum value has nothing to do with k times lk we discussed last Friday. Because if somebody demands k times lk as large as possible, they will not follow this Fibonacci sequence to cut the rope. We can plot the dependence of fm times phi to the power of m plus 2 on m in a figure, so that everyone can get a more straightforward impression. When m is equal to 1, its value is phi to the third power. And when m is equal to 2, it is phi to the fourth power. As m further increases, it rapidly approaches the square of phi over phi plus 1 over phi. Thank you for watching, and see you next time.